To everyone. We'll see about the counters. Counters are one of the most used components in the digital circuits. The input pulses are called count pulses, may be clock pulses, or they may originate from an external source or occur at a prescribed intervals or at random. In a counter, the sequence of states may follow binary count or any other sequence. Counters are found in almost all equipments containing digital systems. So here the counters binary counter. A counter that follows the binary sequence is called as a binary counter. An n-bit binary counter consists of n flip-flops and can count n binaries on count in binary from 0 to 2 power n minus 1. For example, binary counter for 2 digits is as follows. That is 0 0, so next is 0 1 and 1 0 1, the next state is 1 0, and if 1 0, the next state is 1 1 1 1 1 0 0. So it will continues. So examples of, here's another example in a binary counter and its state table. So from 0 0 it goes to 0 1, that is when the input is 0 it goes to 0 1, and if input is 1 it goes to 1 1. If with the 0 1, if their input is 0 it goes for 1 0, if it input is 1 it goes for 0 0. 1 0 input 1 0, if your present state is 1 0 and if your input is 0 then 1 1. Then 1 0, if the input is 1 then it goes for 0 1. Then if the present state is 1 1 and your input is 0 then it goes for 0 0. Then 1 1, if your input is 1 and it goes to the next state 1 0. So this is it. Applications of counters. Some of the applications of counters in a sequential circuits are as follows: to count the number of occurrences, generating timing sequences, count up or down, increment or decrement count, sequence events, divide frequencies, adjust memory as a temporary memory. So two principal categories of counters, that is called asynchronous counters and synchronous counters. Asynchronous counter, it is a ripple counter, and asynchronous counter is also called as a serial counter, is a cascade arrangement of flip-flops when the output of one flip-flop drives the clock input of the succeeding flip-flops. In this counter, the clock input signal is applied only to the first flip-flop, also called the input flip-flop, not for all. Then in synchronous counters, it is also known as parallel counter, in which all the flip-flops are synchronized with the same clock input signal and changes its states at the same time in synchronism when the input clock signals. A delay involved in this case is equal to the propagation delay of one flip-flop only, irrespective of the number of flip-flops used to construct the counters. In other words, delay is independent of the size of the counters. Then few other categories of counters. So that is ring counter, Johnson counter, decade counter, up-down counters. So asynchronous counter. Here flip-flop output transitions serve as a source for triggering other flip-flops. This means that the clock pulse is provided to a single flip-flop. The change of state of a given flip-flop is dependent on the state of the other flip-flops. In other words, the flip-flops are not triggered by simultaneous clock pulse but the transitions in other flip-flops. So the counter is called as the asynchronous counters because not all the flip-flops are the same clock. Look at the waveform, we can say that is in the Q timing diagram, it resembles a clock as well. This provides a clock that runs twice as slow. If we feed the clock entity flip-flops where T is the hardwired to 1, the output will be a clock whose periods twice as long. 2-bit asynchronous counters lives in that the external clock is connected to the clock input of the first flip-flop only. So it changes states the negative edge of each clock pulse. But the next flip-flop changes only when triggered by the negative edge of the Q output of the first time. So because of the inherent propagation delay through a flip-flop, the transition of the input clock pulses and the transition of the Q output of the flip-flops can never occur at exactly at the same times. Therefore, the flip-flops cannot be triggered simultaneously, producing an asynchronous operation. Example as shown, there is some delay between a clock and Q1 transitions. So 2-bit asynchronous counter, usually all the clear inputs are connected together, so that a single pulse can clear all the flip-flops before counting start. The 2-bit ripple counter circuit has 4 different states, each of the corresponding to a count value. Similarly, a counter with n flip-flops will have 2n states. The number of states in a counter is known as mod counter or modulo number. Then a 3-bit ripple counter using a T flip-flops is an example given here. So first only one flip-flop is excited, is given as a clock pulse. Then other flip-flops are triggered by using an output of the previous flip-flops. So in synchronous counters, to eliminate the ripple effect used as a common clock pulse for each flip-flops and as a combined circuits to generate the next state. For up counter, use an increment. Synchronous counter, to eliminate the ripple effects, use a common clock for each flip-flop and a combination circuit to generate the next state. Synchronous counter may be of the following type: up counter, down counter. So here we can say that as the counter starts a counting sequence in step manner, that is from binary 0 to 2n per binary n state. It's called as a step up counter. For example, in a 4-bit binary counter, the counter starts from 0000 to 1111. Then the counter recycles back to 000 and then continues from there. Step down counter means a countdown circuit can be constructed by either simply replacing the negative edge triggered flip-flops with positive edge triggers once or using the Q dash output to trigger the next flip-flops. For example, in a 4-bit binary ripple counter, to make the counter count backward from 4 ones to 4 zeros, we should simply use the Q dash output. Then the counter of this type is called as the 4-bit asynchronous step down counters. So here is an example for a design of a BCD counters. So in design of a BCD counter, it is a binary coded decimal counters. So use a sequential mod to design a synchronous BCD counters with D flip-flops and a state table. The input combinations from 1010 through 11 are considered as a don't care, because in BCD we are having the state from 0000 to 1001, that is 9 decimal equivalent number. So the next state from 000 to it goes from first state 1, then from 1 it goes to 2, then 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, then 9 to again 0. So here synchronous BCD counters, it is designed like that then you are by using a K maps you have to simplify it. So from 10 you have to, that is 1010, you have to put a don't care, and then you have to be use the excitation table of your T flip-flops, and then you have to frame the simplify your table using your K map. So unused state has to be considered as a don't care. So here it is called as the ring counters. The ring counters are implemented as shown, where the output of a flip-flop is given as the input to the next flip-flop except the last one. Here the normal output of the last flip-flop is connected back to the input of the first one. Hence it is called as a ring counter. It is formed in the form of a ring, so it is called as the ring counter. Then here it is called as the Johnson counter. The Johnson counter is also known as twisted ring counter. Is exactly same as a ring, except that the inverted output of the last flip-flop is connected. In ring counter, the Q is connected to the input. Here the Q dash, that is the inverted output of the last flip-flop is connected to the input of the first flip-flop. If it starts from 000, then 100, then 100, 110, 111, 011 and 001, and then sequence is repeated as long as there is an input pulse. Thank you.